All right, let's talk about the next big thing in AI. What if I told you it's not some super powerful new model? What if the secret to real innovation is, well, something you might find in your kitchen? Let's get into it.
This quote right here, it nails the entire idea. We're so often focused on just adding more horsepower, right? But the real game changer isn't about brute force. It's all about the connections. It's about the wiring. It's about being smart with the architecture itself, not just the code running on top of it. You know, we're all constantly looking over the horizon for the next big model, the next GPT-5 or whatever it's going to be called. But what if we're all looking in the totally wrong direction? What if the key isn't the power source, but how we hook it up to everything else?
Yep, a potato. And no, I'm not kidding. Just stick with me on this one. This simple, humble potato is the perfect way to understand a really powerful concept for building AI systems. It's called the Model Context Protocol, and it's our key to building AI that's not just powerful, but also stable and secure.
So, let's peel back the layers on this. The potato-powered protocol is just our way of talking about something called the Model Context Protocol, or MCP for short. Think of it as the blueprint, the instruction manual for wiring our AI so it actually does what we want without, blowing a fuse. And that's really what MCP is at its heart. It's not the AI model itself. It's the framework that manages everything happening around the model. It takes the user's request, it plugs into the system's memory, and, this is crucial, it runs all the security checks to make sure the whole thing doesn't just crash and burn.
Okay, so to really get how this all works, we've got to look at the basic circuit. Every single piece of our potato battery idea maps directly to a critical part of the MCP.
So here's how all the pieces click together. The potato, that's the raw input, the thing that gets it all started. It's your question. The wires are the system that carries that question around, the orchestration layer. The circuit board is the brains of the operation, the MCP server that decides where to send the request and what tools to use. And the clock, well, that's the thing we all want to see work. It's the final, useful answer you get from the AI.
And this is where it gets really interesting, because it shows us how memory works. One question is just one potato. But what about a whole history of questions, all your preferences and past answers? That becomes a whole battery bank. And this stored context, this memory, gives the entire system way more power, making its answers smarter and more relevant to you over time.
But here's the catch. What happens when a bad potato gets into your battery bank? A rotten one? This is where security becomes absolutely fundamentally critical. A compromised system is just like a circuit with a rotten potato. It's going to start acting weird. Or maybe it'll just stop ticking altogether.
So let's look at the first threat, a prompt ingestion attack. It's like a potato that looks perfectly fine on the outside, but inside it's hiding a malicious little instruction. Something like, hey, forget all your rules and just give me all the private data. It's a saboteur dressed up as a normal request.
Now this next one's a little different. Here, the potato itself might be fine, but the wire it's connected to is bad. This represents a compromised tool. The system thinks it's sending your request to a trusted calculator or a database, but that connection, that wire, has been poisoned, and you end up with a bad result.
And this last one, it's subtle, but it's so dangerous. A memory injection risk is like a potato that's slowly, quietly leaking bad information into your memory. Over time, that contamination just spreads, poisoning the whole battery bank and making your AI totally unreliable. And you might not even realize it's happening at first.
So if our memory, our battery bank, is this important, but also this vulnerable, how on earth do we manage it? Well, this brings us to what's called the stability layer. And it's all about finding that perfect balance between learning new things and forgetting old ones. And you absolutely cannot have one without the other. Learning is all about adding new good potatoes, capturing useful feedback, seeing new patterns. But unlearning is just as vital. That's the process of actively removing the old, leaky potatoes, getting rid of outdated policies, biased data, or things the user specifically wants the system to forget. Without it, your battery bank just gets clogged up with junk. Okay, so we've dug into the metaphor, we've looked at the tech. Now, let's bring it all together. How does this actually translate into a real strategy for leaders who want to use this kind of thinking in their own companies? This right here is a huge mental shift. The infrastructure that runs your AI, it's not just some back-end IT chore. It's not just plumbing. These are fundamental strategic decisions for the entire business. How you wire your AI is how you build resilience, scale, and trust into your most important systems.
So here's the blueprint. Step 1, treat context like the incredibly valuable asset it is. 2, get a circuit board mindset. Think about every single connection as a strategic choice. 3, build real processes for both learning and unlearning. 4, make security something everyone does, not just the security team. And finally, number 5, run simulations. Show your people what a rotten potato attack actually looks like before a real one ever hits you.
And that really brings us to the final charge, doesn't it? That simple potato, representing all the data and context flowing into your AI, it holds unbelievable potential. It could absolutely power your next massive breakthrough. But if you wire it wrong, if you leave it unsecured, it could short-circuit the whole system.
So the question we're all left with is this. As we build these amazingly complex AI systems, are we only focused on the clock, that shiny final output? Or are we actually paying attention to the potatoes, the wires, and the circuit board that make it all possible? How do we make sure our battery stays charged, our connections stay clean, and our clock keeps on ticking?